Good afternoon again, everyone. Both previous speakers have stressed out the importance of the enhanced interfacial bond at all scales, macroscale, microscale. In this presentation, I will include results from interfacial bond strength at the nanoscale between the products of cement hydration and the nanomaterials that we use, usually all combinations, nanomaterials like fibers, carbon fibers at the nanoscale, carbon nanotubes, graphene nanoplates. For this presentation, I chose to show you carbon nanofibers at a percentage of 0.3%. So, to repeat what the previous speakers have emphasized, obviously higher interfacial bond strength, especially at the nanoscale, translates into improved mechanical properties at the micro and the macro scale. This is what we see from all testing. I don't think there is any reason to explain this. The whole concept lies on being able to control the interactions between the nanomaterials and the hydration products. In other words, we would like to see an improvement in the length of silicate change. This is also well known as the increase the degree of silicate polymerization. For this study, I am going to evaluate using a new type, unique nano-IR AFM. I'm going to evaluate the chemical composition and the mechanical properties of the interface between nanomaterials and CSH for the first time. And I'm going to use the AFM at its nano-IR mode at the sub-10 nanometer level. At the same time, I'll get the chemical imaging mapping of the interface and running also QNM, and that will give me the mechanical properties at the interface. So this study comes in two parts, because with this particular AFM, we have the capability of measuring the electrical properties at this scale, using another mode of this AFM. So part two, characterization of the electrical properties of the interface, comes from Dr. Davidis in the second part of this session. So, I will be showing you results with two levels of dispersion, two extremes. I will be showing you results of as received, used in cement pastes, as received carbon nanofibers, and also highly dispersed carbon nanofibers in cement pastes at an amount of 0.3%. We specifically used 0.3% as this was proven to be from previous studies the percolation threshold for the particular type of carbon nanofibers, and this increases the final compressive strength, stiffness, and toughness of the cementitious matrix at the macro scale. So we have established that a long time ago. We are able to evaluate the degree of dispersion using the DLS, dynamic light scattering method. And in this slide, I'm showing to you the intensity to particle size distribution of three suspensions. These suspensions are made with as-received carbon nanofibers. So all three of them, you see, they exhibit approximately the same intensity. But what is interesting right here is to notice exactly at the maximum diameter, hydrodynamic diameter that we're able to measure is 475 nanometers, and this diameter is 5 times bigger than the actual diameter of a carbon nanofiber. So, I mean, it's very safe to assume at this point that there is no dispersion. As I mentioned, we use as received. So we measured the dispersion index, and as you can see, that dispersion index of 0.7 corresponds to a polydispersed suspension, polydispersed material. So essentially, we have no dispersion at all. This can also be seen by the high experimental error that we measure in this experiment. Now, if we move to a highly dispersed suspension, I'm showing you the exact same method, DLS, dynamic light scattering, and intensity size curves for using our ultrasonic procedure. And right now, we have moved the diameter. We're able to see the diameter being about 160 nanometers. And we run, again, the same calculations for the dispersion index. Now, I wish I could tell you that I had a suspension that I could categorize that as a monodispersed suspension. Unfortunately, I've not seen many of those, but we are very close. So I'm going to name that dispersion nearly monodispersed, meaning that we have a majority, because you see the very narrow distribution there of particles, individual particles, at the actual diameter of the carbon nanofibers, approximately 160 nanometers, and I do not rule out the possibility that a few of nanofiber aggregates still exist in our suspension. So, moving on to the actual results that we were able to obtain using our AFM, I am showing you here at the 10 nanometer resolution a picture taken from the AFM showing, I think you probably are able to distinguish even the interface between the nanofiber, which is shown at the lighter color at the top left corner of the image, and the CSH, which is shown with the darker color. This is this combination of colors was given to us by AFM so that we can distinguish the different materials that we examine. Now, from this picture, actually, we were even able to measure the diameter of the carbon nanofiber and establish, again, the fact that the suspensions are well dispersed and the nominal diameter of the fiber corresponds to 165 nanometers. Now, I'm showing you the same picture at a little lower resolution at 1200 nanometers, just to give you an overview of the whole area there. You can see the two parts, top and bottom, the CSH, and in the middle, it's the nanofiber itself. You can actually distinguish the external graphite plates, graphitic plates of the nanofiber. You see the highlighted areas there. This is a typical picture of carbon nanofiber. I'm going to take you back to our 10 nanometer picture there, and we chose 3 different areas in this picture. One, the dot you see in the highlighted area, brighter area, corresponds to the typical surface of a CNF. Darker area, which is all the top part of this picture, is the CSH. In between, we were able to recognize the interface between an individual carbon nanofiber and the hydration product. So, as you probably suspect, I'm going to show you results from and I'm going to show you the IR spectra from the nanofiber, from the CSH, and also the interface. Let's start with the CSH. Here you see the absorbance from the IR spectra. Actually, the models like the ones that Konrad has presented previously in the literature have reported a thickness level of the interface. Correct me if I am wrong, Konrad. The interface between the fibers and the CSH should have, let's say, a width of about 2 nanometers, between 1 and 5, in the average of 2 nanometers. So in this particular work, we found the thickness of the interface to be about 2 nanometers. Going back to the CSH, the IR spectrum of the calcium silicate hydrates products. There are 7 characteristic peaks that we normally identify when running an FTIR also, and the NanoIR is an FTIR at the nano level. And I would like just to show you, to give you the characteristic peaks. It's 1 weak peak at 1676. So 1676 is due to the bending vibration of the water molecules from etching guide. 1402, we have symmetric carbonate stretching because of CO2. We have sulfates, 1117, which is again the CO4s, the sulfates. And there are other stretching vibrations at the peaks of 980 and 924. CNF is a little bit different, and I'll show you the differences here. Here you see the CNFs with the green color. Blue was for the CSH. We see the same peaks for CNFs, but there are a few very small differences that make a huge difference for our study. Now, from the insert that you see, we have one characteristic peak that is at 1580, and this is due to the carbon skeletal in plane vibration, a double carbon-carbon bond that is attributed to the presence of the carbon molecules. So there we know that we have carbon, and this is the CNF. But there is an additional peak. There is another characteristic peak, which is the peak at the 1640. And this presents the absorbance wave number curve of the CNF surface, and this is attributed to a new bond, chemical bond, between the carbon atoms from the CNF's surface and the carboxyl groups that came from the use of our superplasticizer that we used during sonication. So there is a distinct difference between the spectra between the as received and the functionalized carbon nanofibers, and this meaning before and after sonication. And this difference, you see here the red corresponds to the dispersed CNFs, while the blue corresponds to the CNFs without any dispersions. And can you see the peak there that we see and the difference between the two IR? Nothing is, the two spectra lies one on top of the other, but that peak, the peak at the wavelength of 1640 is the one that creates the different, and it shows the interaction of the carbon atoms at the surface of the carbon nanofiber with the carboxylate ions due to the attachment of the carboxyl groups. Now, at the end, I'm going to show you the interface between the two materials, carbon nanofiber and CSH, the hydration products. Now, the spectrum of the interface is presented in the red curve, and now the peaks here are the same. However, what we observed is that two of the peaks have suffered a shift. Now, I'm not sure if the word suffered is the right one for this purpose, because what I'm going to show you, zooming at this particular area that we see the shift, well, this shift is actually reported in the literature as the blue shift. And the blue shift, it's all new to me because I've never seen a blue shift before, but the blue shift is the characteristic peak that is giving us an indication of the degree of the polymerization. So clearly, looking at these results, we see that at the interface, looking at the part where we have the functionalized CNFs, we managed indeed to increase the polymerization degree, increase the silicate chains, hence an increase in the mechanical strength is to be expected. Now, there is, I believe there is a second shift peak that is showing the same thing. So we do have another characteristic peak that indicates the conjugation between the carbon-carbon and the carbon-oxygen bonds at 1640. And this also appears to be shifted towards lower wave numbers. And this, we assume, that can be attributed, not sure, 100% sure, but we believe that this can be attributed to a stronger bond between the carbon and oxygen molecules, that this bond is able to absorb near infrared light at a higher frequency, hence the observed blue shift. But we are still working on this. This is an ongoing study, so we will have results about this in a future presentation. If we examine the spectra of very quick of similar pastes without containing any functionalized CNFs, and the same thing happens when we include carbon nanotubes. We observed the absence of the characteristic peak that shows that at 1640, which obviously indicates the presence of nothing new, no chemical bonds, nothing. So this is pretty clear to us that functionalization takes place only after a sonication procedure or any other procedure that can ensure a high level, a high degree of dispersion. Now, that was for the 1640. We get the same results for the at 1014, no shift, no any blue shift. So we have no indication that we have any change in the degree of polymerization in the distributed chains of the calcium CSH. Now, as I mentioned in the beginning, one of the main advantages of using the NanoIR AFM is that at the same time we can do also a QNLF mapping of the modulus of elasticity. So what I had shown you for the three areas that we examined for the nanofiber, the CSH, and the interface, I'm going to show you exactly now for results for the modulus of elasticity using the QNM mode at the exact same areas. Now, we calculate the Young's modulus using an equation that is suggested for this particular cases. Now, what you see in this slide, the two figures that you see, one in the left, to the left corresponds to CSH, and the other corresponds to carbon nanofibers. And what we are showing is the normalized force to indentation curves. And we calculate the modulus of elasticity according to the equation. As expected, CSH shows very low stiffness, shows high elastic deformation, about 25% of its deformation. Looking at the picture to the right of this slide, it shows the modulus obtained for the carbon nanofibers. We see a huge difference. We see modulus of elasticity calculated reaching of about 100 gigapascal, and also extremely low error bar we have for this particular measurements. Results are pretty consistent while calculating this modulus of elasticity. And now I'm going to show you the results from the interface. Now, please notice that the elastic deformation of the interface now has moved to 19%. So it's different than the elastic deformation that we measured for the CSH. Of course, does not compare it with the CNF, but I mean, certainly it's improved. And we were able to calculate a modulus of elasticity of about 20 gigapascal. Again, the error that we measured is very small. It's 3%. So results are pretty consistent along different measurements along the this interface. Very consistent between individual CNFs and the hydration products. As mentioned previously, I was never able to obtain a monodispersed suspension using the method of sonication for my carbon nanotubes and carbon nanofibers, even graphene. So, but I showed you results of suspensions very close to monodispersed particles. If you want to see the difference between the as received nanomaterials, it's huge here, and we conducted the exact same experiments, and we have found a high elastic deformation, more than 2 times higher. This indicates to us a very weak interface between the nanomaterial and the CSH. The modulus of elasticity that was calculated was 9.6, 10, half of what we calculated previously. And I think that one other indication is that we see a large scattering of the results. Here you see the error here is about 22%. In the previous slide, it was 3%. So again, it doesn't compare. So taking into account all this results, the results from the NanoIR and the results of the QNM, I believe it's safe to assume that dispersion is absolutely required, no matter if we reach the monodispersed, let's say, level. But without it, this is crucial to enhance the interface between the nanomaterials and the hydration products, and that will lead us to enhanced properties at the micro and macro scale. Eventually, if we go deep down, we can measure the degree of the polymerization. I'm sure Conrad would like to run a few calculations using actual results, and we will take it from there. I would like to thank you for your attention for this presentation, and Dr. Danoglidis in the next session will give you results of the electrical properties at the interface. Thank you very much.